Hi class, we continue our study in Chapter 12 by moving into our final section of Chapter 12, which is Section 12.5, talking about equations of lines and planes. In this video, what I want to do is I want to talk about how you find the equations of lines. This is really important in three-dimensional space. So if you think about it, in two-dimensional space, the equations of lines was just y is equal to mx plus b. But in three-dimensional space, that's no longer sufficient, right? So three-dimensional space has the x, y, and z coordinates, where that equation just doesn't have the z in it. Okay, so a line in the xy plane is determined when a point on the line and the direction of, the direction of the line, its slope are given. So the equation of a line can then be written using what I described as that point slope form. Likewise, a line L, this is what we're going to be investigating, line L in three-dimensional space is determined when we know a point, so an initial point, okay, x0, y0, z0 on the line, and the direction of the line. Okay, so how are we going to find the direction of the line? Well, in three dimensions, the direction of a line is conveniently described using a vector, right? Vectors have direction in them, okay, direction and magnitude. So we let vector v, some vector v, be a parallel vector to the line, okay? So here's what I want to describe. Here's this line, L. I want to find the equation of the line. And just in the previous setup, what we have here, here's the line. Here's the initial point on the line, okay? And this is the vector v that's parallel to the line. So this vector is pointing in the same direction as this line, okay? So what we're first going to do is let some other point P, just defined as x, y, and z, be some arbitrary point on the line. So I have 2 points on the line now. And I'm going to let r sub 0 and the vector r, okay, be the position vectors of the points p0 and p respectively. Okay, so r sub 0 is this vector that goes to the original vector, and vector r goes to just the arbitrary point. Okay, if vector a, this one here, is the vector represented by p sub 0 to p, okay, then what we see by the triangle law, okay, is that this vector r is equal to r sub 0, our initial vector, plus this vector a between them. Okay, that's really important right there. Okay, but since a and v are parallel vectors, there is some scalar t such that a is equal to tv. Okay, so thus, this vector r is equal to r sub 0 plus some scalar times our parallel vector v. Okay, which is what we call the vector equation of the line L. Okay, so that's one equation. That's the vector equation. All right. Each value of the parameter t gives the position vector r of a point on line L. In other words, as t varies, the line is traced out by the tip of the vector. Okay, so what you can see in figure 2 indicates positive values of t move the vector up the line, negative values of p move vectors down the line. Okay, if the vector v that gives the direction of the line L is written in component form, okay, as vector v is equal to a comma b comma c, all right, then we have this t times v is equal to ta comma tb comma tc, all right. So we can also write r as being equal to the vector xyz and r0 be equal to the vector x0 comma y0 comma z0. So the vector equation becomes the following. Okay, this is the vector equation for the equation of a line. All right, x, y, z, the vector point of the line is equal to the initial point plus some t times a, which is the value of the a component of the parallel vector, y sub 0 plus t times the b component of the parallel vector, and z sub 0 plus t times c, which is the c component of the parallel vector. Okay. So therefore we have the following three scalar equations, okay? So these are scalar equations for a line. X is equal to x sub 0 plus a times t, y is equal to y sub 0 plus b times t, and z is equal to z sub 0 plus c times t, okay? These equations are called the parametric equations of the line L through the point p0, so this is the initial point, and parallel to this vector, okay, ABC. So basically what I'm saying here is if you know an initial point and a parallel vector, these are the parametric equations for the line. Okay, and each value of the parameter t will end up giving you a point on the line. All right, so the parametric equations of a line through the point x0, y0, z0, and a parallel direction vector a, b, and c are just the following. Okay, so those are the parametric equations. All right, let's do an example of this. So let's find a vector equation in parametric equations for the line that passes through the point 5, 1, 3, and it's parallel to this vector. Okay, so this is vector v, which is really 1, 4, -2. All right, and then what I want to do is I just want to find two other points on the line. Okay, so the first thing we need to do is find the parametric equations for the line. So r sub 0 here is my point, 5, 1, 3. All right, and my parallel vector v is equal to this 1, 4, -2. Okay, so looking back at our first equation here, initial vector, all right, or vector to the initial point, our parametric parameter t times the parallel vector. Sorry about that. So r, okay, which is the vector form of the equation, is equal to the point vector plus the parameter times the parallel vector. So now you just combine like terms basically. So this is 5 plus t times I, 1 plus 4t times j, and 3 minus 2t times k right here. So then what you can say, the parametric equations are just x is equal to 5 plus t. That's this part right here, the x coordinate. Y coordinate is equal to 1 plus 4t. That's this part right here. And z is equal to 3 minus 2t. That's this part right here. Okay, so that's the parametric equations for the line. So now it just said to find 2 points on the line. So all you have to do is just pick values of t. Okay, like if you pick t is equal to negative, or t is equal to 1 and plug it in, you get the point 6, 5, 1 as a point on the line. And similarly, if you pick the value t is equal to -1, it gives the points 4, -3, 5. All right, so next, if we stay at the point 5, 1, 3, but choose the parallel vector 2i plus 8i minus 4k, we arrive at these equations right here. Okay, 5 plus 2t is equal to 1 plus 8t, and z is equal to 3 minus 4t. So in general, a vector v is used to describe the direction of the line, and then the numbers a, b, and c are called the direction numbers of L. Okay, since any vector parallel v can be used, we see that any three numbers proportional to a, b, and c can be used to describe the set of directions for the lines. Okay, so if you kind of look what's happening here, 1, 4, -2, 2, 8, -4, we just doubled the values of t. That's really all that happens, and that doesn't matter. Okay, another way of describing a line L is to eliminate the parameter t from the equation. Okay, so if none of a, b, and c is equal to 0, so we can solve each of these equations for t. So just take these equations and solve them for t, and you get t is equal to x minus x0 over a, y minus y0 over b, and z minus z0 over c. But that's what all t is equal to. So all you're going to do next is set these equations equal to each other, and you have x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. All right, this right here is called the symmetric equations of the line. So just looking over here, right, like if we just take our parametric equations and solve them each for t, we get x minus 5 is equal to, this should be, y minus 1 over 4 is equal to, subtracting the 3 and then dividing by the 2, z minus 3 over 2. And that's another way you can represent these.